Let's design Chapter 9, Design a URL Shortener. We'll start by nailing down the system requirements, and we do that through a candidate and interviewer exchange. The candidate kicks things off by asking for a concrete example of how a URL shortening service actually works. The interviewer gives us one, take a long, unwieldy URL like https://www.systeminterview.com/q=chatsystem_v=v3 $L=, the kind of URL nobody wants to type or share. The service maps that to a short alias like https://tinyurl.com/y7kocwj. You open the alias, and you're redirected to the original URL. Simple idea, interesting engineering challenge. The candidate then asks how short the shortened URL should be. The answer, as short as possible. That's an important design constraint we'll need to keep in mind when we think about encoding. Next up, what characters are allowed? Numbers and letters only. And can shortened URLs be updated or deleted? For simplicity, no. We're treating them as immutable once created. With that context established, we can define the functional requirements in terms of API endpoints. A URL shortening service really needs just two. First, a post endpoint at API/v1/data/shorten. This accepts a long URL and returns a short one. Second, a get endpoint at API/v1/short-URL. This takes the short URL and returns the original long URL for HTTP redirection. Beyond those functional requirements, we also need high availability, scalability, and fault tolerance. Now, that get endpoint raises an interesting question: which HTTP redirect status code should we use, 301 or 302? The difference matters more than you might expect. A 301 status means permanently moved. It tells the browser that this short URL will always point to the same destination. The browser caches that mapping, so on subsequent visits it skips the URL shortener entirely and goes straight to the original URL. A 302 status means temporarily moved. The browser treats the mapping as potentially changeable, so every time someone clicks the short link, the request goes back through the URL shortener service before reaching the destination. So which do you choose? If reducing server load is the priority, go with 301, you're essentially offloading repeat visits to the browser cache. But if analytics matter, if you need to track how many times a link is clicked, when, and from where, then 302 is the right choice, because every click passes through your service and can be recorded. Now let's talk numbers. The interviewer gives us a load of 100 million URLs created per day. Divide that by 86,400 seconds in a day and you get roughly 1,200 write operations per second. Assuming a read-to-write ratio of 10 to 1, that means about 12,000 read operations per second, which makes sense, since people click links far more often than they create them. If we expect the service to run for 10 years, we need to support around 365 billion records in total. Assuming an average URL length of 100 characters, the storage requirement over that 10-year period works out to approximately 36.5 terabytes. That's a meaningful number that will shape our storage and database decisions. Let's talk about core entities. In a simplified version of this system, you might reach for an in-memory hash table to store your URLs. That approach has two serious problems. First, memory is finite, so you'll eventually run out of space. Second, anything stored in memory is lost the moment the server restarts, so you have no persistence. To solve both of those problems, we use a simple relational database table instead. A single table with a few columns is all we need. It gives us durability and scales far more predictably. Now let's think about the hash value itself. The characters we allow are 0 through 9, lowercase a through z, and uppercase a through z. That's 62 possible characters per position in the hash. The question then becomes, how many characters do we actually need? We want the shortest hash that can still accommodate our full URL space. The math we need to solve is 62 to the power of n, which must be greater than or equal to 365 billion. When you work that out, n equals 7. A 7-character hash drawn from those 62 characters can theoretically support around 3.5 trillion unique URLs, which gives us plenty of headroom beyond our target. Now let's talk about API design. We're going to build a REST API, which gives us a clean, stateless interface that's easy to work with over HTTP. For a URL shortening service, we really only need 2 endpoints. The first is a post request to API/v1/data/shorten. This is the endpoint responsible for creation. You send it a long URL, and it hands back a short one. We use post here because we're creating a new resource on the server. The second is a GET request to API/v1/short URL. This one does the heavy lifting for redirection. Given a short URL, it looks up and returns the original long URL so the client can be redirected to the right destination. GET makes sense here because we're simply retrieving existing information without changing anything. You'll also notice both endpoints are versioned under v1. That's intentional. It gives us the flexibility to evolve the API later without breaking existing clients. Now let's walk through the data flow. Starting with URL redirecting. When a user visits a short URL, we need a way to look up the original long URL and send them to the right place. The simplest and most performant way to implement this redirection is to store the short URL and long URL together as a key-value pair in an in-memory hash table. Because the data lives in memory, lookups are extremely fast, which matters here since redirection is the most frequent operation in this kind of system. Now let's look at URL shortening. To support shortening, we need a hash function that can take a long URL and produce a compact short URL, and critically, we also need to be able to map back from that short URL to the original. Here's how the full workflow comes together. When a user submits a long URL, a unique ID is generated for it. To make sure that ID generation works correctly across multiple servers in a distributed environment, we use Twitter's Snowflake algorithm, which guarantees unique IDs without any central coordination. That ID is then used to produce the short URL, and the mapping is stored in the database. On the read side, when a user clicks a short URL, the request first hits a load balancer, which forwards it to one of the available service instances. The service then checks the cache. If the short URL is already cached, the corresponding long URL is returned immediately without touching the database. If it's not in the cache, the service fetches the long URL from the database and stores it in the cache for future requests. And if no record is found at all, that simply means the short URL doesn't exist. Now let's walk through the high-level design. Starting with URL redirecting. Let's look at how the flow actually works. As you can see in the diagram, when a user submits a short URL, the request hits the server, which looks up the corresponding long URL and redirects the user to it. The simplest and most effective way to implement this is to store the short URL and long URL as a key-value pair in an in-memory hash table. This is fast because hash table lookups happen in constant time, making redirects nearly instant for the end user. Next, URL shortening. To support this, we need to find a suitable hash function. The hash function has to do 2 things: take a long URL and map it to a short URL, and then be able to map that short URL back to the original. Choosing the right hash function matters a lot here. It affects uniqueness, length of the generated short URL, and how efficiently we can handle collisions. The specifics of how we design and evaluate that hash function will be covered in the detailed design section. To summarize what we've covered in the high-level design, we looked at API design, the data model, the hash function approach, URL shortening, and URL redirecting. Now let's get into the deep dives. Starting with the hash function. Our short URLs will be made up of characters from 0 to 9, lowercase a to z, and uppercase a to z. That gives us 62 possible characters per position. To figure out the minimum length we need, we solve for n in 62 to the power of n being greater than or equal to 365 billion. That gives us n equals 7, and a 7-character hash can support roughly 3.5 trillion URLs, which gives us plenty of headroom. Now, for the actual hash function, there are 2 main approaches: hash plus collision detection, or base 62 conversion. With the first approach, you'd use something like MD5 or SHA-256, but only take the first 7 characters of the output. The problem is that truncating a hash like this introduces the possibility of collisions, two different long URLs producing the same short URL. To handle that, you rerun the hash with some padding appended to the input and keep trying until you find a value that isn't already taken. The catch here is that every attempt requires a database query to check whether the value is already in use. Bloom filters can help with this. They let you quickly check if a value probably exists without hitting the database every time. The second approach is base 62 conversion. Instead of hashing, you take a unique numeric ID and convert it into a base 62 string. Since the ID is unique by definition, collisions are simply not possible. Let's compare these two approaches directly. With hash plus collision resolution, the short URL length is always fixed. It doesn't depend on a unique ID generator, which simplifies the infrastructure. But you do have to handle collisions, and because the output doesn't depend on an incrementing ID, you can't predict or enumerate short URLs, which is actually good for security. With base 62 conversion, there's no collision risk, and you skip the extra database lookups. But the URL length isn't fixed, it grows as IDs get larger. You also depend on a unique ID generator. And importantly, if your IDs increment by 1 for each new entry, it becomes easy to guess the next available short URL, which is a real security concern. Moving on to the URL shortening deep dive. Given those trade-offs, we're going with base 62 encoding to keep things straightforward. Here's the full workflow. A long URL comes in, the system generates a unique ID for it, that ID gets converted to a 7-character base 62 string, and that becomes the short URL which is then stored in the database. To make sure the ID generator works correctly across multiple machines in a distributed environment, we use Twitter's Snowflake algorithm, which guarantees globally unique IDs without requiring coordination between nodes. Now let's look at the URL redirection deep dive. Since reads massively outnumber writes in a URL shortener, we introduce a cache to improve read performance. The flow works like this: a user clicks a short URL, the load balancer routes the request to one of the service instances, the service checks the cache first, if the short URL is there, it returns the long URL immediately. If it's not in the cache, it falls back to the database, stores the result in cache for future requests, and returns the long URL. If the short URL isn't found in the database either, then it simply doesn't exist. There are also a few additional talking points worth covering. A rate limiter is a good addition to protect against malicious actors who might try to flood the system with shortening requests. On the web server side, scaling is straightforward because the service is stateless, you can just add more instances behind the load balancer. For the database layer, replication and sharding are the standard approaches for scaling out. Analytics is another valuable consideration. Tracking how many users clicked a given link, for example, gives clients meaningful business insights. And of course, availability, consistency, and reliability are fundamental to any distributed system. We'd apply the concepts covered in Chapter 2 to address those here. Let's get into the wrap-up. In this chapter we covered 5 core topics. First, API design, defining the contract between clients and our service. Second, the data model, thinking through how we structure and store our URL sufficiently. Third, the hash function, the mechanism at the heart of generating short, unique keys. Fourth, URL shortening, the end-to-end flow of taking a long URL and producing a shortened one. And fifth, URL redirecting, how we resolve a short code back to the original destination and send the user on their way. Beyond those fundamentals, there are several directions worth exploring if you want to push the design further. On the topic of a rate limiter, without one, a malicious actor could hammer our shortening endpoint with enormous volumes of requests, exhausting resources and potentially generating junk data at scale. A rate limiter sits in front of the service and enforces a ceiling on how many requests a single client can make within a given window. For web server scaling, because our service tier is stateless, meaning no session or user data lives on the server itself, we can spin up additional instances behind a load balancer whenever traffic grows. Statelessness is what makes horizontal scaling straightforward here. For database scaling, as our URL mappings grow into the hundreds of millions, a single database node becomes a bottleneck. Replication improves read throughput and provides redundancy, while Shortener distributes the dataset across multiple nodes so no single machine carries the full load. On analytics, embedding tracking into the redirect flow gives clients genuinely valuable signals, like how many users clicked a particular link, where they came from, and when. That kind of data can drive real business decisions, so it's worth designing for it early. And finally, availability, consistency, and reliability are foundational concerns for any distributed system. The strategies for tackling those were covered back in Chapter 2, and everything discussed there applies directly here.